This section explains what a network is and why so bare a representation carries the whole chapter. A network is nothing but points, joined in pairs, nodes, and edges, and the chapter's entire wager is that this near-empty representation is enough. Strip the internet, a food web, a citation graph, a friendship down to who connects to who. Discard everything the nodes materially are, and the systems become the same object. What survives the forgetting is structure, and structure predicts function. That is the generative move the entire book runs on. Identical adjacency, different substrate, shared behavior, so a result proven once transfers across every domain at once. The 4 families. Newman names technological, information, social, and biological are not a taxonomy. They are proof of reach. One abstraction, and the sciences collapse onto it. This part explains why engineered networks, of all things, have no blueprint to read off. Engineered networks are the one place you would expect a blueprint to exist, and it doesn't. That is the chapter's whole move. The internet, the power grid, transport and delivery systems are built by many uncoordinated hands. No central authority dictates their shape. The IETF writes protocols, not topology. The IETF writes protocols, not topology. So the structure has to be measured rather than read off a tine. This is the first of Newman's 4 cataloging chapters, and it plants the book's empirical root. Observational data is the starting point for everything downstream. Even the tidy picture, the internet as 3 concentric shells, backbone, then ISPs, then end users, is a discovered regularity, not a mandated one. The object is defined by what probing reveals, never by intent. This part explains what makes a network informational rather than physical. A network becomes informational when its edges denote reference, one item pointing at another because of what it means rather than where it sits. That single move fixes the type. Reference is asymmetric, so these graphs are inherently directed, and that is what severs them from the physical internet of Chapter 2, with its symmetric cables, even though both carry data. The web's hyperlink and the paper citation are one object seen twice, a node emitting arrows at the nodes it invokes. The chapter's quiet surprise is that the boundary is fuzzy. Email and social graphs, deferred to Chapter 4, are reference and acquaintance at once. Predict the rest, any corpus that cites itself is this graph. This section introduces what a social network is and where its data really comes from. A social network is any graph whose nodes are people, the actors, and whose edges are some chosen relation between them, friendship, exchange, sex, sitting on the same board. The chapter's real primitive is that the edge is a decision, not a datum. Unlike the internet or the web, a human tie leaves no automatic trace, so the network must be elicited, and the eliciting instrument constructs the object it measures. Consider the forms this takes. Moreno's hand, drawn sociograms, direct questionnaires, archival guest lists, as in the Southern Women's Study, read as a bipartite affiliation network. Change the question, change the edge, change the network. This is the first substrate where the data is human-made rather than machine-logged. Measurement choice and error are intrinsic here, never noise to be cleaned away. This section explains the single representational move behind the whole chapter. Biology becomes a network the moment you choose what counts as a node and what counts as an edge, and wildly unlike systems collapse onto one formalism once you do. Metabolites joined by reactions, neurons joined by synapses, species joined by who eats whom. 3 biologies, 1 graph. Newman's placement is deliberate. This is the last of the empirical chapters before the mathematics, so its job is to show that the formalism is substrate agnostic and that the genuinely hard biology lives not in the graph, but in measuring it. The structure must be reconstructed experimentally, reaction by reaction, before any network exists to analyze. This section explains how the entire study of networks starts from one move, turning a network into a matrix. That single move is what the chapter installs. Label the end nodes, then set the entry aij to 1 whenever an edge joins node I and node j, and the entire object, friendship network, food web, power grid alike, collapses to the single matrix A. Structure becomes algebra. Graph questions become linear. Algebra questions, and every measure the later chapters read off, degree, paths, centrality, is just a function of A. Here is the tell that the encoding is designed rather than merely recorded. A self-edge sets the diagonal entry, AII to 2, where you would expect 1. Each edge owns 2 ends, so counting the 2 ends of a loop keeps the arithmetic consistent. Once you see that the diagonal is chosen to make the arithmetic clean, you can predict every downstream convention. The representation is the theory. This section explains how a chapter's worth of network measures reduces to a single generative move. A network's adjacency matrix holds everything, yet tells you nothing directly. The chapter's whole job is the map from that matrix to a scalar, boiling structure into numbers a human can rank. Centrality, transitivity, and modularity are 3 such projections. But the generative move surfaces in eigenvector centrality. Define a node's importance as proportional to its neighbor's importance. The circularity that looks like a vicious regress resolves itself. The measure is the dominant eigenvector of the adjacency matrix, a fixed point. That is the primitive to carry. A self-referential measure over a graph collapses to a spectral quantity. Once you see importance defined by importance become an eigenproblem, PageRank, CATS, and Hub authority scores are all the same move, retuned. This section explains why the storage form of a network decides the cost of everything you compute on it. Every measure defined in the earlier chapters, centrality, components, path lengths, is a function on a network. This chapter is where those functions stop being definitions and become things a machine runs on millions of nodes. The generative primitive is this. The storage representation fixes the cost of every downstream computation. Store the network as an n by n adjacency matrix and you pay order n squared just to exist. Store it instead as an adjacency list, each node keeping only its actual neighbors, and cost scales with edges, not with n squared. Real networks are sparse, so the list wins decisively. Predict the rest from this. Any algorithm's running time is read off the representation you chose before writing a line. This part explains why every network you measure is a noisy readout of a network you cannot see. The chapter's move is to stop treating the adjacency entry, a sub ij, as an observed bit, and to treat it instead as a latent variable, with your repeated measurements as noisy samples governed by a true positive and a false positive rate. Once an edge is latent rather than observed, the apparatus is forced. The ground truth network and the error rates fall out jointly by maximum likelihood, and each edge exits not as a 0 or a 1, but as a posterior probability. This is Newman's quiet correction to the field. A network reported without error bars is an anomaly the discipline has normalized. Measurement error earns the same standard, deviation, and p-value treatment you would never omit for a voltage or a drug trial. This section explains what falls out when every measure from the toolkit is pointed at empirical data. The same handful of regularities appears regardless of substrate. Film actors, the web, metabolism, and power grids all answer alike. The regularities are these. One large component swallows most of the nodes. Typical distances stay tiny, scaling as the logarithm of n, which is the small world effect. Degree distributions are fat-tailed, often power law. Clustering runs far above chance, and degrees correlate with those of their neighbors. The chapter's move is to read these as a shared statistical basis. Knowing that a network is real-world predicts its profile better than knowing what it is made of. This is universality, established empirically rather than derived. Table 10.1 is that argument in one object. 24 unrelated systems and a single set of columns that fits them all. This section explains the random graph, the null model at the base of network science. Start by throwing away every structural fact about a network except one number, its mean degree, and connect each pair of nodes independently with exactly the probability that reproduces that number. What remains is the maximally random graph consistent with that single constraint, and it is exactly solvable. This is why the chapter anchors the book's modeling arc. It is the null against which every real netters the book's modeling arc. It is the null against which every real network structure registers that reproduces that number. The surprise is that structure here is emergent, never assumed. As the mean degree crosses 1, a giant connected component crystallizes out of a soup of small fragments, a percolation transition living inside pure randomness. To predict the next model, ask which constraint you refuse to discard. This section explains the configuration model, and its whole move is a single constraint. Fix only the degrees and randomize everything else. That one restriction is the entire chapter. The random graph of chapter 11 fails because it forces Poisson degrees, which do not match the right-skewed degree distributions of real networks. The configuration model frees the degree distribution while keeping maximum randomness everywhere else, and that is why it stays exactly solvable. The generative primitive is the stub. Give node I exactly ki half edges, where ki is the degree you want that node to have, and then pair the stubs uniformly at random. The chosen degree sequence is guaranteed by construction. Uniformity over matchings means that any stub is equally likely to meet any other stub, and that homogeneity is precisely what maps the modal analytically to meet any other stub, and that homogeneity is precisely what wakens the stubs uniformly at random. This is the same maximum entropy logic as the Poisson graph. Pin the one feature you care about, and let entropy fill in the rest. This section explains how network models flip the direction of every prior chapter. Every prior chapter fixed the degree distribution and studied its consequences. This one inverts the arrow. You posit a growth rule and derive the distribution as its attractor. The generative primitive is proportional feedback. New nodes attach to existing ones with a probability that rises in the degree those nodes already carry. This is Simon's rich. Get richer. Price named it cumulative advantage, and Barabasi and Albert renamed it preferential attachment. Linear preference has a power law as its fixed point, and the exponent falls out of the attachment rate alone. That reframing carries the whole chapter. Structure becomes something you run forward and watch precipitate. Hold that idea, and any heavy tale you find in the wild poses one question. What growth rule has this as its equilibrium? This section explains community structure, the partition a network carries without ever being told to. A network hands you a grouping it was never asked to hold. Nodes clump into blocks that are dense within and sparse between, and those blocks are real organization. Research groups in a co-authorship graph, ethnic cleavage in a friendship graph, functional units in a metabolism. The generative move is that this mesoscale structure sits above the node and below the whole, and you recover it rather than impose it. You infer it against a null where edges fell at random, so a community is any excess of internal density over chance. This is the book's pivot from measuring structure to using it. Once you can find the blocks, a million-node graph collapses to a legible sketch, and the graph's own connectivity tells you where its seams lie. This section explains percolation and network resilience as a single structural primitive. Cut a random fraction of a network's nodes and ask one question. Does a giant connected component survive? That single order parameter, the fraction of nodes still mutually reachable, is what the chapter names resilience. It collapses at a threshold occupation. Probability, written phi-c, rather than degrading smoothly, a phase transition of the same kind as freezing or magnetization. Function is reduced to one structural quantity, connectivity under attrition. Router failure, vaccination, and herd immunity are one process read at opposite valuations, the knock-on effect of a single removal propagating through shared paths. The generative move is this: do not ask which nodes matter. Ask when the whole loses its backbone. Everything downstream is which removal rule reaches phi-c fastest. This section explains how epidemics become a percolation process once you take them off a fully mixed crowd and put them on a network. Drop the fully mixed assumption of Chapter 15, and disease stops spreading through an undifferentiated crowd. It starts spreading along the edges of a contact graph. The instant you do this, an epidemic becomes a percolation process. One translational move carries the whole chapter. An SIR outbreak equals bond percolation. Transmissibility plays the bond. Occupation probability, the giant cluster, plays the epidemic, and the percolation threshold plays the epidemic threshold. So everything the degree distribution did to percolation, it now does to contagion. A heavy-tailed contact structure drags the epidemic threshold toward zero, and herd immunity recedes out of reach. Now predict the adjacent case yourself. Whatever destroys a giant component, which is targeted removal of hubs, is exactly what halts the outbreak.